it's good. Good.
Thank you. Okay. So last time we were talking about vibrational energy transfer, and we used this simple model where we have a collinear system where an A atom is colliding with a BC molecule along the internuclear bond axis. And we assumed a trajectory where the A atom has a constant velocity, but it, after impinging on BC, then it turns around and goes the other way. And so this is the expression that we arrived at using time-dependent perturbation theory. So the probability of going from some initial vibrational state I to some final vibrational state F after the collision, it's given by this expression here, where you have a overlap integral between e to the minus the velocity of the A atom times absolute value of time over rho, where rho is this parameter that describes the distance of the interaction. Right? This is the distance over which the interaction potential falls off. And then that gets multiplied by e to the I omega t, where omega is the frequency of a photon that you would need in order to excite the transition from the initial state to the final state. So it's just the energy difference divided by h bar. And so one way that you can think about this expression is this integral here. This is actually a Fourier transform. So this is the Fourier transform of e to the minus vt over rho. And so in order for this probability at a particular omega to be non-zero, e to the minus vt over rho has to have a frequency component at omega. Right? And so this e to the I omega t, if you take the absolute value of this looks like a oscillatory sine wave, right? And so, you know, this is oscillating at some relatively high frequency, right? Usually vibrational frequencies are high compared to, you know, the motion that's associated with translational collisions. And so this function e to the minus v absolute value t over rho, this has to have some frequency component at a high frequency that matches omega, right? And so I drew these on the board the other day. So this function here looks like an exponential decay on either side of 0, right, with a distance parameter given by rho, right? So here's t and here's the function. So this distance here is rho. And then this function here, if you sketch it, if you sketch the absolute value of it, then it basically just looks like a sine wave. And so basically this function here has to have some frequency component that matches this sine wave. So if the velocity is very fast, right, or the rho is very small, right, then you're going to have a sharp peak, and it's going to have some high frequency component, and the transition is going to be lightly. But if rho is, you know, if the interaction distance is very long, or if the speed is very slow, then this curve here is going to be only sort of weakly peaked, right? And then you're not going to have so many high frequency components, and the transition probability is going to be low. Okay? Right, and so this is what we sort of said at the end of the last lecture. So there's this adiabaticity parameter, so the probability is, you know, if you analyze this expression in the limit of low transition probability, you can write it as the exponential of minus xc, where xc is this adiabaticity parameter equal to 2 pi omega rho over v. And so you can think of this as, well, 1 over omega, that's the period of vibration, right? So, and then rho over v, that's sort of the characteristic time over which the collision takes place. And so this is you could write it as 2 pi times the time that it takes for the collision divided by the time that it takes for a vibrational period. And so the collision time, so in order for the transition to be likely, this xc has to be small, right, because it's exponential of minus xc. And so the collision time, right, the time of the collision has to be small relative to the vibrational period. So, you know, if you want a classical example, if you've ever, you know, played with a guitar, right, if you pluck a string, you know, and let it go really quickly, then the string will ring, it'll vibrate. But if you were to, you know, like pull the string away from its equilibrium and then slowly let it go back to its equilibrium and then let it go, then the string would no longer vibrate. You wouldn't hear the tone of the guitar. So it's the same principle. Basically, the time for striking the string has to be fast compared to the vibrational period, otherwise you won't excite the vibration. Okay, just a couple more things that I want to say. Okay, so you know, how does this depend on the range parameter rho? So if the range parameter is long, right, long interaction range, then would you expect the excitation probability to be high or low? Yeah, exactly, because then it's like the case where, you know, if the guitar string can feel my finger from far away, then the interaction is long and it's kind of gentle. Whereas if the range parameter is very short, then it's like a harder strike that the vibrating molecule is going to feel. Okay, there's also orientation effects. So this C parameter here, recall this should be in your notes. The C parameter is should be A times this vibrational overlap, or the matrix element of the R operator, times gamma times e to the gamma times equilibrium distance over rho. And then this gets divided by rho, which is the distance of the interaction. Okay, so yeah, so when would you expect more vibrational frequency? So let's say B is really heavy and C is really light. Would you expect more excitation if the A atom collides with B or with C? If B is heavy and C is light? Yeah, I think intuitively you would say C, right? But mathematically, what's the reason for that? Sorry? So what's this gamma parameter equal to? This was gamma. Gamma was equal to the mass of C divided by the mass of B plus mass of C. Is that right? Mm-hmm. Yeah, so if C is really light, right, and we were assuming in this model that A is colliding with the B end of the molecule. So if C is really light and B is really heavy, then this gamma parameter is really small. But if it's the other way around, then the gamma parameter is really big. And so it's kind of like, you could imagine if you took a bowling ball and attached a spring to it and then attached a ping pong ball, right, and then threw a tennis ball at it, then, you know, if the tennis ball hits the ping pong ball, then it's probably going to cause the spring to vibrate. But if the tennis ball hits the bowling ball, then probably no vibrational excitation. Maybe you can make the whole thing translate a little bit, but you're probably not going to compress the spring, right? This is just a classical physics consideration. Okay, so I guess I can write that down. So orientation effects. So if MC is much greater than MB, then the probability of excitation is high. But if MB is much greater than MC, then in that limit, the excitation probability goes to 0. Okay? And so one more thing, I won't do the integral on the board, but you can take this result and average it over the Maxwell-Boltzmann distribution of speeds, V, right? So basically you take an integral of this result times the Maxwell-Boltzmann probability of each speed. And if you do that, then the result that you're going to get is the probability of excitation is going to be exponent of -3 times 2 pi to the 4th mu times nu squared. This nu is the frequency, this is the linear frequency of the vibration, right? So it's 2 pi omega over rho squared, this is the interaction distance parameter, times kT. Okay, and then I'll just show you some experimental data. Any questions while this is coming up? Loading. Okay. Okay, so here's some experimental data on the probability of vibrational relaxation of HCl by collision with helium or argon. So here's when you take HCl and V equals 1, and this is the log base 10 of the probability of a collision with helium or argon taking the HCl molecule down to V equals 0. And so you can see the probability is proportional to temperature to the -1/3, as you would expect based on this relationship here. And it's also very low. So you know, at 300 Kelvin, which is somewhere here, the probability is something like 10 to the -6 or 10 to the -7. So it takes many, many collisions in order for the vibrational relaxation to occur. However, there's some data for this other experiment here involving CO2 with 1 quantum of antisymmetric stretch vibration, and it's being relaxed by collisions with nitrogen. And this has a much higher probability of relaxation, as you can see. At high temperatures, it looks like it follows this T to the -1/3 trend, but at lower temperatures, the trend is actually the other way around. So what's going on here? So actually the answer is that the relaxation mechanism in this case is different than the one that we've just discussed. So we've been discussing transfer of basically vibrational energy to translational energy, right? Because we're talking about an atom colliding with a diatomic molecule. But in this case, it's a molecule colliding with a molecule. And it just so happens that the N2 vibration has a frequency that's very close in energy to the antisymmetric CO2 stretch, so that it can relax by this mechanism here. So CO2 in the excited vibrational state can collide with nitrogen molecule in the ground state to produce CO2 in the ground state plus nitrogen in the first excited V=1 state. And the leftover amount of energy is only 18 reciprocal centimeters. And so this is the amount of energy that gets released as a translation. And so in this case, omega is a very low frequency, right? Because the frequency difference, right, the energy difference between the final state and the initial state, if you consider the internal states of both collision partners, is only 18 wave numbers. So even at very low velocities, you can transfer this amount of energy, right? Right, so this function here will have some component at that frequency, because it's a low frequency. And also, you can see that the relaxation probability actually increases somewhat with at lower temperatures. That's because in this mechanism, basically a vibrational energy is being coupled to a vibrational energy, not to a translational energy. And the probability of this transfer actually increases if the interaction time is a little bit longer. It's kind of like if you take a guitar string and play it really close to a piano string and let the resonance of the guitar string excite the piano string, right? If this interaction lasts a little bit longer, it's more likely to transfer the vibrational energy. Okay, questions? Okay, so that's all I wanted to say about vibrational energy transfer. And the next topic that we will discuss is rotation. And I'm going to be somewhat brief about rotation. So we can use the same general theory, and if you consider the probability of a transfer of rotational energy, right, so translational energy to rotational energy, then the probability of being in some final state at t=infinity, right, this would be, according to our perturbation theory result, 1/IH bar times the integral from -infinity to infinity of the time-dependent perturbation, right, due to the collision, times e⁻⁻I initial energy minus final energy times t/h bar. And then this integral is with respect to dt, and then you take the absolute value and square it. Okay? And so, in the case of vibrational energies, if you have a harmonic oscillator, the vibrational levels are evenly spaced. But in the case of rotational energy, usually the rotational energy levels are much closer together, right? Because the rotational constant is usually very small compared to the vibrational constant. And also, they increase quadratically with the quantum number j. So the rotational energy, if you have a rigid rotor, goes as the rotational constant times j plus 1. And so if you sort of plot the energy levels, they start out close together, but then they get quite far apart because the energy increases quadratically with j. Okay, so if we consider sort of the same idea of the adiabaticity parameter, right, the time scale for the collision versus the frequency, right, omega IF equals EI minus EF over h bar. Then at room temperature, there are typically many J states that are occupied. And so a collision can be adiabatic, which means it's slow compared to the rotational excitation frequency. And that's going to be the case if you're at high J, right, where the spacing between the levels is high, right, so this omega is going to be high, or if delta J is high, or large. Right, so if you're going from like J equals 0 to J equals 10, then you're likely to be in the adiabatic limit where the excitation is unlikely. But you can be not adiabatic if you're at low J, where the energy levels are close together, or if you're considering a small delta J. Okay, does that make sense? Can you see this? Do I need to get stuff out of the way? Okay, any questions about that? So I'll quickly show you some data. So shown here, this is a plot of experimental measurement of the likelihood, if you're starting in different initial J states, which final J state do you end up in after a collision. So if you start in an initial J state of 2, then there's actually a very high probability that you'll end up in some other state, right? So these probabilities are high. That's because at J equals 2, the level spacings are close together, and so the probability of the collision time being short compared to the period of oscillation of this omega frequency, that's going to be a high probability. And the highest probability is to go from like J equals 2 to J equals 3, right? And as you increase the final J, the probability decreases. That's because the spacing between the levels, right, which determines this omega, starts to get big as you go to high J. Okay, if you start in some other initial state, like let's say you start in initially J equals 26, then you can either relax or excite due to a collision. Overall, the probability is smaller because at J equals 26, the energy levels are farther apart. But it's not so unlikely to change J by plus or minus 1 or plus or minus 2, right? It would take about okay, well this is in units of per density, right? So this is a second order rate constant. But then as you go to very high J, the probability of being able to relax or excite the rotation due to a collision starts to get much smaller, right? Because at high J, the level spacing is very far apart. Okay, any questions about that? Okay, so our final topic for this section on energy transfer is going to be electronic energy transfer. Okay? And so in order to illustrate electronic energy transfer, so that's transfer between electronic energy and translational energy during a collision. In order to illustrate this, we'll consider an example. Where we have two excited states of the calcium atom. So we're going to put calcium in the singlet P1 electronic state, and it's going to undergo a collision with helium, and then there's a certain probability that the calcium atom can relax to the slightly lower lying electronic state triplet P1. These are both excited states. Okay, so what is the meaning of these different states? Well, if you look at the sort of orbital energy diagram for calcium in the ground state, who knows what the configuration of calcium is? Where are the outer electrons located? Which orbital?
Forest.
Yeah, exactly. So in the ground state, you have a 4s orbital, and it's doubly occupied, right? In the singlet P1 state, however, you take the calcium atom and you excite one of the electrons to a 5p orbital. So in the singlet P1 state, it looks like this. You have a 4s orbital, and then higher in energy, you have 5p orbitals. And it's a singlet state, so what does that mean about if I draw this spin up, then the other spin has to be up or down?
Down.
Down, right, because it's singlet, so the total spin is 0. Okay, and then there's a state that's slightly lower in energy with the same configuration, except this spin is going to be a triplet, so that means the two spins are in the same direction. And Hund's rules tell you that if you have the same configuration, the one with the highest spin multiplicity is lower in energy. So that would tell you that this triplet P state is going to be slightly lower in energy than the singlet P. So this one, you could draw it like this. You have a 5p orbital, and the spins are going to look like that. Okay? So that's the idea. You excite calcium to this level, and then it can undergo a collision with the helium atom, and it has some probability of relaxing to this state, right? So the spin flips, and there's an energy relaxation. Okay, so we're going to draw. What does that look like? Okay, so what if we draw the energy, or sketch the energy, versus the distance between the calcium and the helium atom? So we can call that R calcium helium. Right, so at very large distances, you're going to have some separation. That's just due to the energetic separation between the singlet state and the triplet state. So at some higher energy, you're going to have calcium in the singlet P1 state plus helium. And at some lower energy, you're going to have calcium in the triplet P1 state plus helium. Okay? And now, what happens when helium comes in and collides with calcium? So helium, right, it's a noble gas. It has a completely filled second or first row of the periodic table, right? So it does not want to do any bonding with the electrons of the calcium. And so one thing I haven't mentioned is that there's 3 different 5p orbitals, right? There's a 5px, 5py, and 5pz orbital, and they are degenerate. So you could excite the electron to any one of these 3 orbitals, and they are located along a different axis in space. And so if the orbital that you excite the electron into, if it's pointing towards the helium atom, then you can form like a sigma interaction orbital, and that one is not stable. So the sigma state goes up in energy, right? Because the helium does not want to accept electron density from a calcium. But if the orbital, the 5p orbital of the calcium is perpendicular to the helium atom, right? If the helium atom is coming in like this and the p electron is like this, then there is a small amount of stabilization, and you get a pi molecular orbital interaction. Okay, and the same is true of the calcium in the triplet state. The only difference is the spins are different, but the interaction is the same. So you also have a sigma and a pi. Okay? And so, let me label that pi. Okay, and so there's a special feature of this energy diagram, and that is there's a curve crossing here. And so as we mentioned when we were talking about interaction of different electronic states, right, non-adiabatic interactions, these level crossings are very important because that's where non-adiabatic dynamics can take place. In other words, you can hop from one potential energy surface to another if they're very close together in energy, such as what would happen here at a crossing. And so you can consider a non-adiabatic scattering trajectory where you start out in one electronic state and end up in a different electronic state. And in order for that to happen, so one example of how you could do that is if you come in on the pi binding state, and then let's say the first time you follow the diabatic curve, this pi curve, right? So you come in like this, and then at some energy, you don't have enough kinetic energy to go any further, so you have to turn around. And then let's say the second time that you go through this crossing, let's say you end up going on the lower adiabat, so jumping to the other diabat, and you go to the sigma state, which correlates to the triplet calcium product. So this would be an example, right, in red, of a non-adiabatic, what we would call a non-adiabatic trajectory. Okay? And so experimentally, this collision system has been investigated in a crossed beam experiment done by Steve Leone at Berkeley. And basically you take an atomic beam of calcium and an atomic beam of helium, and you can excite the calcium to this singlet P1 state using a linearly polarized laser. And depending on the polarization of the laser, you can excite different 5p orbitals. So if you turn the polarization, you can change from exciting the electron from a 5px to a 5py to a 5pz, right? The p orbital direction is going to be determined by the polarization direction of the laser. And then they can measure this relaxation probability. And actually the way they do that is they measure the kinetic energy that gets released into the helium atom. And depending on, and it has a strong dependence on the direction of the polarization of the laser. So you can see, if you look at the relaxation probability as a function of this angle, then you get a low probability when the angle is 0, meaning the orbital is oriented towards the colliding helium atom, right? It has a component along the relative velocity direction. And you get the highest relaxation probability when the orbital that you excite is perpendicular, right? So that means if it's parallel, that means you follow the sigma curve, right? So that means there's no interaction with this curve, so the transition is unlikely to happen. But if it's perpendicular, then you follow this curve here, and then there's a curve crossing, and that means you're more likely to have a non-adiabatic interaction. Does that make sense? Okay, so let's analyze in a little bit more detail what's going on. We're going to consider what is the probability of a non-adiabatic transition and basically I'm going to do a very simplified derivation of what's called Landau-Zener theory. Okay, so let's say you take this graph here and you zoom in on this interaction region here. Right, so then if you plot the energy versus distance, then you have these two diabatic curves. I'll call them 1' and 2'. And as we talked about when we were talking about Born-Oppenheimer theory, you also have these non-crossing diabatic curves, which I'll plot in red, and I'll call those 1 and 2. Right, so in red, we have the adiabats, right, 1 and 2, and in black, we have the diabats. These are 1' and 2'. Okay, and we can define some parameters. So let's say the minimum separation between these adiabats, let's say that occurs at a position R0, and the energy separation, right, from here to here, we'll call that E0. And let's say that also there's an interaction distance, and we'll call that rho. Right, so that's the characteristic distance over which these two diabats interact with each other and separate in energy. Okay? And so according to the theory for non-adiabatic transitions, if the system goes through this crossing region very slowly, then since the electron velocities are much, much higher than the nuclear velocities, right? The electrons sort of have time to adjust, and you would tend to follow the adiabatic curve, right? Where you go from one electronic state character to a different electronic state character, right? 1' to 2', right? Singlet to triplet. Whereas if you go really fast through this region, then you can have non-Born-Oppenheimer behavior where this approximation that the electrons are going fast relative to the nuclear motion, it's no longer true anymore. And so if you go really fast, you can end up staying on the singlet curve or the triplet curve. Right? You stay on the diabatic curve, on the black curve. Okay? So let's assume, we're just going to make an assumption that this delta, the distance between, the difference in energy between the two adiabats right, let's say that that is approximately given by the average energy separation between the two diabatic curves over the region of interaction. Okay? So we can express this average as an integral. So the E naught then would equal 1 over the distance times the integral of the function. Okay? And if you zoom in close enough, then these diabats are going to basically look like straight lines, right? The closer you zoom in, the less curvature you're going to see. You can approximate it as a straight line. And so if you write this in terms of a straight line, let's change coordinates so that we're in coordinates of x, where x is 0 at the crossing. Then we could write these as, this would be 1 over rho times, we're going to go from minus rho over 2 to rho over 2. And this curve here, this is just going to be a slope times x, right? Because it goes through 0 at x equals 0. So times x minus d v2 prime dx, right? And so this is equal to, so these slopes are just constants because we're assuming that these are straight lines. So we're going to get the difference in the slopes. That's a constant. We can take it out of the integral. And then we get the integral from minus rho over 2 to rho over 2 of absolute value of x dx. Right, and this integral, so this one, we're going to call this difference of slopes delta f. And this integral here, if you do this integral, this is just equal to rho squared over 2.
Is there a missing x in the second line, second equation?
Yeah. Yeah, slope times x is the equation for the line. Okay, so that means we're almost out of time, but we're almost done. So basically, this difference in energy, I'll call it delta E naught. This is 1 over rho times delta F times rho squared over 2, right? Or to simplify that, it's just rho times delta F over 2. And so that means if we solve for rho equals 2 times the energy difference between the curves over delta F. And if we plug that into so if you say that the probability, again, it's proportional to this exponential of minus xc, where xc is equal to let's see, it's 2 pi times omega rho over v, right, where omega is just difference in energy over h bar. And so we can plug in our result here for rho, and also plug in omega equals delta E over h bar. And then we're going to get that this P12 is going to be proportional to exponent of minus 4 pi delta E naught squared over h bar times delta F times the velocity. And this was a very simplified derivation of Landau-Zener theory. The actual Landau-Zener theory says it gets a slightly different constant here, but the probability is equal to the exponent of minus pi squared times the energy difference squared over h times delta F times velocity. Okay? And so this is the probability each time you cross. If you have a trajectory where you cross 2 times, right, like the one I showed, one crossing, second crossing, one of them has to be adiabatic, one of them has to be diabatic. So the overall probability of a non-adiabatic transition is the probability of making a hop the first time times the probability of not making a hop the second time. Times 2, because there's 2 ways you can do it. You can either hop, not hop, or you can not hop, hop. Okay, and we're kind of out of time, but any questions?